So we'll talk about noise first and then go to nonlinear distortion separately. So noise levels, I guess the term is very familiar for you guys already. Noise is due to random fluctuations. So when you measure a circuit, you will get like something called white noise. Most you guys might be familiar. So if you look at this frequency spectrum, if it's white noise, it'll just pop up. It'll have random values, but maybe there's a like sort of an average level. Now this will determine your detectable signal. So if you can't really detect something below the noise level, there are ways to detect some things below the noise level. Things like such as GPS actually detects things below the noise level, but then you need to have the algorithms right to pretty much retrieve the information if you are below the noise level. So now understanding noise, how it originates, is more like a physics course, so we don't really cover those stuff. That's more in physics. As an engineer, you just need to know how the noise behaves, how do we characterize it. So noise can be generated within the circuit itself, and then can be like due to cosmic events like environmental, blackbody radiation. Now there are few types of noise, more than what I listed here, but something that comes across very frequently is thermal noise, so which is a random white noise as it's shown here, and it's caused by the random movement of charge carriers in a resistor. So any resistor, any circuit will have this thermal noise. Now if you want to, so the nice thing about this noise is, like, I mean, it is random, right? So you can't really point a value and predict it. This is going to be my noise value at this time. It's hard to say that. But if you want to find the noise power, there's something about this noise when you actually look at the mean. Like if you square the noise, which is you get everything positive, and then look at the mean over a certain period of time, that's called the average pretty much, that remains same. So you can predict that part. Okay, so this is what it says. So if you integrate that noise, squared of that noise from minus t by 2 to plus t by 2 and divide by t, you get average value. And that average value you can actually predict. And that once you predict it, that average value turns out to be something called KTB. Now the K is called Boltzmann constant, and the T is the temperature in Kelvin, and the B is the bandwidth in Hertz. Now what's interesting here is this is pretty much bandwidth and temperature dependent. It's not depending on your resistance value. Right? So you can have a 10 ohm resistor, you can have a 1 mega ohm resistor, still the noise level that the thermal noise it generates is pretty much determined by this. So you can have like pretty much zero noise power at Kelvin 0, right? Absolute zero. So you won't have any noise. So that's why you actually want to, sometimes circuits won't operate at close to Kelvin 0. Absolute 0, that means because it has very low noise levels, right? So that's the reason why you won't operate at low temperature. And superconductors, you need to cool it down, right? So that's pretty much the same reason as well. The B is the bandwidth, and that means the higher the bandwidth, higher the noise, average noise level. Other than that, you can have different types of noises called flicker noise, which is really not really important for the RF designers because this happens at low frequencies. I'm just listing them because just for you guys to know, but you don't really have to know the physics because as a designer you will never use those physics anyway. The short noise is when you actually when you have is pretty much, it's similar to, it's a white noise as well. Short noise is created depending on your DC biasing current. So when you use higher DC voltages in your circuits, you can have a higher short noise. That's why you tend to have like every circuit working at very low voltages now, like lower and lower voltages. One thing is V times I, your power consumption is lower and your short noise is lower as well. Now, as a designer, what's more important for us is how do we really characterize that. So there was something called noise figure that you must be familiar with. roughly, at least heard the term of. But noise figure and noise factor is the two things that a designer must know. Noise factor we normally denote it by F, and noise figure NF. So the factor, by the name, as the name implies, it's just a ratio, right? So in here, signal to noise ratio, in any circuit you can calculate the signal noise ratio at the input and output, right? So you look at the signal to noise ratio at the input, divide by signal to noise ratio at the output. And if you have that to be equal, SNRs, which means F equals 1, right? So if this and that equals F equals 1, that means that's pretty much a noiseless circuit. I'll come to that in a minute. Now, okay, so let's say if you find the noise factor, you look at the 10 log of that, and that becomes a noise figure. Okay. Now it's easy to deal with noise figure because it is in dBs, and you can actually, when it's multiplied, you can just add them because it's in log, right? Okay, now we'll probably try to make sense of these equations here, just because it needs to, you can remember, you don't need to know the derivations, you can remember, but I think if I do the derivation, maybe it might be slightly more insightful for you guys, just at least to remember the equation. Well, you don't even have to remember, you have open book exam, so you can bring it, okay? And, right, so if you have, so if I want to find the noise, so this is the noise into the circuit, and then you have excess noise generated within the circuit, could be thermal noise, short noise, something. But in this case, we are pretty much looking at thermal noise. That's what we can characterize as KTB, right? And then you can have a total noise out at the output. So your total noise would be noise input plus excess noise, right? Now, if I read F, which is the noise factor, that's SNR at the input divided by SNR at the output, which means signal input divided by noise input divided by signal output divided by noise output, right? So I can write this as SI over NI times NO or SO. So we need to sort of simplify this a bit more. So SI over NI times signal output would, if the circuit has a gain of G, so your signal output would be gain times the signal input, right? And your noise at the output would be gain times the noise at the input plus some excess noise, because the excess noise is within the circuit, so it doesn't get amplified. That's plus. So if I simplify this, SI cancels out. The GNI plus NE divided by GNI. So that becomes 1 plus NE over G times NI. Right? So that's this. So your excess noise, so your noise factor, if you know the excess noise and your input noise, you can pretty much determine that. Okay, so that's the derivation of that. So if I want to find the total noise now, so maybe this equation is not really right. Noise input output is not equal to noise input plus noise excess. This is equal to noise input plus gain times noise input plus excess noise. So if I rewrite that, NO equals, instead of NE, I can actually get from here, I can say NE equals F minus 1 times GNI, right? From this. So I can now write, instead of NE, this as F minus 1 times GNI GNI. So when I simplify that, I will get G. Okay. So that's the noise output, because GNI cancels out with minus GNI. So if you look at this part, that's pretty much the amplification of the noise, and that's the noise factor. So you can calculate your noise output by gain times noise input times the noise factor, right? So that's why it was defined as F. And you can now see the value of this as a noise figure, because if you look at if you do log to the both sides, you do 10 log noise 0, 10 log. So that's just F. You can write this as 10 log F plus 10 log GNI. So that's the, and O you can write pretty much plus 10 log NI. So this is pretty much noise figure plus the gain plus the noise input, all in dBms or dBs, becomes your total noise. Okay. Now, so that's just a derivation. You just need to remember the equations. Now, there was another in our lab 1. We did a question in AWR simulator. I think you found the total gain of the system, right? Remember, you guys plotted the gain with different components. And then I think there were some questions, how do you calculate the gain with multiple cascade circuits? Okay, so we use a formula called Friis formula. Now, we can derive if you want, but I don't think it's really important at this stage. You need to remember the equation. So the equation comes in the terms, so if you want to find the noise figure of a cascade system, you will have say in this case, the first, so G1 is the gain of that circuit, F1 is the noise factor, G2 is the gain of the second circuit, F2 is the noise factor of the second circuit. Now, if I want to find the noise factor of the complete circuit, which is this thing as a whole, I can find that with the gains and noise factors of each of the components in there. So, for example, if you think this circuit has only two circuits inside, so G1, and I want to find the noise factor of the circuit, I can use this formula, which is T equals 2, right? So that means F of this circuit is F1 plus, so I have only two, this is actually T, I have only M equals 2, so N equals 2 to M equals 2, I will get F2 minus 1 G1, right? So this is the noise factor of the complete circuit when you have two circuits. So what happens if you have three circuits? It becomes F3 minus 1 G1 G2. If you have more, it becomes F4 minus 1 G1 G2 G3. What you'll notice is the noise factor pretty much depends on the noise factor of the first circuit, and the second, third circuits aren't really critical because they will get divided by the gain. So this number will be a smaller number. These things will be smaller. So the first circuit that comes at the front of the complete circuit will determine your noise factor. Okay. Now the Friis formula is important because you need to know that especially when you want to cascade. So we'll do a question. So this question is important because this is similar to a question that you guys will get in the exam. Okay. So so I've broken it down to pieces so it will be easier to digest. So there's an amplifier with a gain. So the gain, so there are two pretty much amplifier and filter. So basically you will connect this to an antenna in a receiver, right? So it could be your LNA and this could be a filter. So in the idea of the filter is that you will, so you filter out. So in your example, if in your example you have 12 to 16 gigahertz assessment 2, right? Amplifier. So what happens when you get a signal from the antenna, you will have a broad band. So apart from 12 to 16, your circuit will amplify, LNA will amplify everything. You will have constant gain here, but it will still amplify things around in the surroundings, right? Right. So what you need to do is you need to filter out these parts, remove the adjacent signals when you give it as the output, because the adjacent signals will actually interfere with the other sub-circuits from here onwards, right? You don't really want to do that. So that's why you use a filter. We call this a band pass filter, called BPF. If you're pretty much passing a band. So the filter can be a band pass filter. So if this axis is S21 and this is frequency, right? Band pass filter will have a response like S21 response. S21 can only be 0, so you will have a response because it's a passive device. You will have a response like that. So that will pass the band in that. But normally when you actually denote that as a band pass filter, you will say band pass filter that's a band pass filter, and a band stop filter you will say it's a band stop filter because it stops this band here, right? S21 and that's 0, that's 0. So it could be a band pass filter or it could be a low pass filter, which is passing everything and then not passing things afterwards. It could be a high pass filter, it's not passing anything. So this is similar to inductor, because usually you pass everything at the low frequencies and then you tend to be high impedance and then it doesn't pass. This is some additional content, but it will be useful. Okay. Now, in this case, we don't worry about the function. We just we have you can have the filter before and then the amplifier after, or you can have the amplifier and then the filter. Now, so the first thing is, what is the gain of the filter? Now, filter has a loss, right? Insertion loss of 3 dB. Now, so insertion loss, or IL, is pretty much equals to S21, absolute value of that. Okay? So the gain of that, in that sense, it doesn't have a gain because it's an insertion loss. So the gain of the filter would be minus 3 dB. Whatever the loss is your gain. Right, so that's your A. So in here it's minus 3 dB. So any passive device, whatever the loss, will become your gain, which is minus, right? And what is the noise figure of the filter? So the noise figure of a filter, filter is a passive device pretty much, right? So whatever the power in, whatever the noise in, input and output is all matched to 50 ohms, right? So your noise figure by default will be your insertion loss. So you notice your gain is your negative insertion loss, which is minus 3 dB. Your noise figure is this is positive 3 dB. So if you think about this, a filter will have a 50 ohm matched, and then the filter and a 50 ohm match. Right? So your noise doesn't get really divided, so whatever the noise comes out, right? Because you don't really have any noise generation inside. So your noise figure is pretty much your insertion loss. So A and B is quite easy. Now, what is the overall gain of the cascaded system shown in figure A and B? So the amplifier has a gain of 20 dB, and we found the gain of the filter as minus 3 dB. So what is the total gain of the circuit? 17, just adding that, right? Because your powers just multiply, and then it's very easy. So exam questions, not that hard, right? Okay, just have to think straight. So 17 dB. So is it different for this circuit? Is it going to be different? Any difference? This is minus 3 dB, it's 20 dB. So it's the same gain, right? So gain would be same. So that's the, see, what is the noise factor of the cascaded system shown in figure A and figure B? So let's find it to figure A first. So this might take a while. So your noise factor of a cascaded system is given by the Friis formula, right? So that's formula. So if it's a two circuits, so what is your F would be F1 plus F2 minus 1 over G1. Okay? Right. Now I want to find F1. So let's find for circuit A, right? Circuit A. So I want to find F1 first. So the amplifier noise figure is 2 dB. So what is my F1? How do I find F1? So noise figure is 10 dB, right? So noise figure 2 dB is 10 log F, right? So that means my F would be 10 to the power noise figure divided by 10. So that means my F1 would be 10 to the power noise figure 2 divided by 10. Okay, so that's 10 to the power 0.2. Can you find the answer? What is it? Point something? 1.55. That's 1.58. So remember, this is, so if it's factor, you need to convert noise figure to the factor, right? So we found F1, we know that. We want to find F2, right? So what is F2? Again, 10 to the power 3 divided by 10, right? And what is that? 10 to the power 0.3. Is that clear? Because 3 is our noise figure for the filter, so I'm finding the noise factor. Sorry? 1.99. So I know that. I want to find G1. So G1 is the gain of the first circuit, which is 20 dB. Now I want to convert this to again. So G1 is the gain, which means I need to convert it to from log to the decimals. So I will have to find 10 to the power 20 over, and that's 10 to the power 2, which is 100, right?
What happens if it's a negative?
Sorry?
How do we calculate if the gain is a negative?
So the gain will never be in dBm. because gain is a difference. A power can be dBm because the power is, so dBm means, so when you have a dBm, it only means, so dB is the power ratio, right? So you have a P1 over P2 and then you get 10 log P1 over P2. And if P2 with respect to 1 milliwatt, you will say dBm, right? Otherwise, your ratios, when you divide powers, you will not have milliwatt or anything, pretty much, right? So you'll just have a value because units cancels out. So you have a dB, you have a difference. So gain will never be in dBm, it will always be in dB. So you got the all the values. So now I find, just sub in that values, 1.58 plus F2 is 1.99 minus 1 divided by 100. Right? Okay, so that's your noise factor. Okay? So that's a cascaded system noise factor for circuit A. So let's do this for circuit B as well. So same formula, right? But in this case, F1, so this is for circuit B. So in this case, F1 would be my filters noise factor, which is 1.99, right? And F2 would be the amplifier's noise factor, which is 1.58, right? And my gain, which is G1, would be 10 to the power minus 3 over 10, right? So that is 10 to the power, and what is that? 10 to the power minus 0.3. Point 0.5, right? Yeah. Okay, so now if I sub in the values, so F equals 1.99 plus 1.99, plus 1.58 minus 1 divided by 0.5. 1.99 plus 0.58 divided by 0.5 times it by 2, 1.04 or 6, 1.16. I'm depending on you guys. Is that 1.16? Yes. Okay. So then add them up. A 3.15 or something? Yeah. So in the second case, you notice the noise factor is very high compared to the first case. So you don't really want that because that means you will increase your noise factor, additional noise, right? That's because of the filter's gain. Filter has a loss, so it pretty much actually, additional noise it provides will really make things worse. The gain of that circuit is negative, right? So ideally you would prefer the filter to be after the amplifier rather than having it before the amplifier.
Doesn't the amplifier also amplify the additional noise?
Yeah, but then you filter it out.
So isn't it better if you filter it first and then amplify?
In terms of gain, it's better if you filter it out first. and then, but in terms of noise, when you receive at an antenna, you'll receive very low signal anyway. So it's okay, like even if it's a broadband signal, you can amplify it and then filter it. But if you are receiving a very high signal, you probably want to have filter first, because you're not worried about noise. You already have a higher signal, right? So in that case, you prefer a setup like this, like when you already have a higher signal, because you don't worry about noise. But at the receiver front end, you don't really want to have a filter. You'll just pretty much have an amplifier first, and then the filter it out. That's because of this noise figure, noise factor. Okay, clear? So that's important that you guys sort of, if you have any questions on this, just ask me, because this is very similar to exam questions you are getting. Is it clear?
So the mid-band gain, the first question?
Yes.
The mid-band gain will be far from the insertion loss?
So mid-band gain is pretty much loss, negative of insertion loss, because it doesn't have a gain because it's a filter. Filter doesn't have, it has a loss, so the gain becomes minus 3 dB. That's why. And your noise factor is exactly the same as your loss. See, this is valid for all passive devices. But when it comes to amplifiers, you can't really just get the gain and inverse it. You can't really do it. You just have to calculate. Or someone has to give you the noise factor. Okay, so now the noise figure, the last part. Maybe I'll do it over here. That's E. So noise figure is, once you have the noise factor, it's easy to do. It's 10 log F, right? So 10 log 1.5899. This is for circuit A. Other one is 10 log 3.15. Okay, so I guess the first one is very similar to 2 dB, because it's, I guess it's 2.01 or 02 maybe. So this one and that, you need to find, can you find the values? Sorry, 2.0. So 10 log 1.5899. What is it? 2.01. And the other one, 10 log 3.15. 4.99. So you can see the difference that in dBs, it's almost double, right? In dBs, you can't really say double because it doesn't make much sense. So 2.01 dB, if you notice, that's very similar to the amplifier's noise figure, which is 2 dB. So it didn't really change much. Right? Is that clear? So the amplifier, whatever the noise figure, remains as it is for the whole circuit, because amplifier pretty much, because in your noise figure calculation, noise factor calculation, F1 is the first component of noise factor, and the whatever the rest will get divided by a gain. So it's very small number. See this one, this is a very small number compared to the first stage, F1. Okay? Is that clear? So far, any questions? So go through this example again, because it will be useful. Yeah, so this is something very like, it's hard to prove it. You can prove it, but for any passive device pretty much don't generate any power, right? So it doesn't have a gain for sure. So its gain of that passive device would be whatever that loss you measure, which is S21. So for a filter, you S21, and there's a term called mid-band gain, right? Because this mid-band gain is, because when you talk about a gain, you don't know whether the gain is at that mid-band or start of the band or out of the band. Out of the band, obviously, you'll have a different loss, or maybe you'll just pass. Maybe your gain is 0. In the mid-band for a filter, you will have whatever the insertion loss it has, which is 3 dB, right? So the gain in this case equals minus insertion loss. That's why I had to do minus 3 dB. Now, noise it adds is the loss it generates, right? The loss itself is 3 dB. That becomes your noise. That's your excess noise. And that's why here I said noise figure equals insertion loss. And that's, but it's a straightforward thing. There's no justification pretty much you need to write when you derive it. And remember this, for a filter, your gain would be minus insertion loss. Your noise figure would be your insertion loss as it is. Did I make it clear? Any passive device is the same. So if you have a 3, I'll go back to the slide before, and maybe I'll delete this one. If you have 3 circuits with gains and if you have 3 circuits, first circuit with F1, G1, and the second circuit with F2, G2, third circuit with F3, G3, what is your total noise figure, noise factor from this equation? Because just remember, I was only doing the two circuit noise factor for 2 circuits. So you will have F1 in here, F2 minus over 1 or G1, plus the other one becomes F3 minus 1 over G1, G2, right? It goes on like that. Okay, so if you have 3 circuits in the exam, that's how you should work it out, right? So you need to find F1, F2, F3 if it's not given, and then G1, G1, G1. So this is not in dBs, okay? Remember, G1, G2 is not in dBs. You need to convert it back to the power level gain in decimals.